the AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, and welcome everyone. Welcome back to AI for Climate Science. We're kicking off again after a bit of a break with a fantastic set of speakers, which are roughly every 2 weeks, so you can find it all in the program. But today we're super excited to have our first speaker kicking off, Sarah Shamek, and who will speak about convective organization and new machine learning approaches to this. So just a quick background and bio. So Sarah has done an undergraduate degree in physics in Tehran, in Iran, and then went to the International Center of Theoretical Physics in Trieste in Italy to work there, and then did a PhD at LMD in France, and is now a postdoc at Columbia University. And exciting news, we'll soon start a faculty position at NYU, I think from January 2024. And today, Sarah will talk about machine learning insights into precipitation, implicitly learning a cloud organization for improved predictions. And I'm very excited to hear talk. Over to you.
Hi, can you see my slides?
Yes.
Okay.
Not the right view yet.
Yeah, okay. Thanks so much for introducing me. I'm very excited to be here. I'm going to talk about our work on machine learning insight into predicting precipitation by predicting or by implicitly learning a cloud organization. So I'm Sarah Shamek. This is a collaboration with my colleague at Columbia University, Dr. Carl Lamb, our PhD student Yu Wang, and Professor Gentin. Just reduce the size of the image. Okay. So to mention a little bit about the motivation of this work, what we can see from climate model is that they have kind of very persisting bias in predicting precipitation. So here I'm showing the plot that shows the frequency of occurrence of precipitation in y-axis for the plot on the left, and then the cumulative contribution to total rain in percentage on the left. And in the x-axis, I'm showing the rain rate. So this plot compares observation data in the solid line with the precipitation predicted in climate model from NOAA GFDL. So in the dashed line, for example, which is a very typical parameterization for deep convection, what we can see is that the model has a very strong bias in predicting precipitation. For example, it overpredicts a small rains, so the rain rate that has values smaller than 1.5 millimeter per hour are predicted like 5 times more compared to what we have in observation. While for precipitation that has a stronger values, the model underestimates the frequency. For example, for rain rates of values larger than 2 millimeters per hour, the model has 1 degree of magnitude underestimation of the frequency. Now we can play with this parameterization to improve a little bit the prediction of precipitation. However, the model cannot really reproduce the distribution of that we can observe in real world. So overall, what we can observe in climate model is that they have a bias to rain too often and too little. They overpredict light rain. So how they have this bias to toward light rain. And they have a smaller variance compared to what we observe in real world. So that's basically sets the motivation for this work. And so the way that I'm gonna continue my talk, I'm gonna first start by introducing the clouds and precipitation in observation and in high resolution simulation. Then I'm gonna talk a little bit about how GCM models precipitation and deep convection. Then I'm gonna go through objective. I'm gonna talk about the neural network methodology and the data that we use. And then I'm gonna discuss some of the results that we have. Okay, so let me start by showing an image of the Earth taken from the satellite. What we can observe are clouds. So they are everywhere. They're ubiquitous, and they get really different pattern and different form at different spatial and temporal scale. For example, here we can see this large scale cloudiness that is pretty much uniform. But if we zoom in, we can also observe very rich and very, let's say, different patterns in our cloudiness. Now, some of these patterns, they happen very frequently. This paper, for example, by Stevens et al., they collected a large set of satellite images from clouds, and they used human to classify those images. And what they found is that these 4 patterns happen very frequently. So they have given like specific names to those specific patterns. And what they find is that each of these patterns has its own specific atmospheric profile. And once they form, they have a very strong footprint on the radiative properties of the atmosphere. The different pattern or different, what I call organization or degree of organization, is not just a matter of shallow clouds, which is the case for these 2 images, but for these 4 images, but it's also a very important property of deep convection, because specifically for this work, we are interested in precipitation, and most strong precipitation are associated with deep convection. So again, in this image, I'm showing the brightness temperature of the clouds of deep convection. And what we can observe is, again, that convection can be very scattered or very, let's say, randomly distributed, but they may also form some very strong cluster. And that has been shown to have a very strong impact on precipitation. So I'm going to refer to the cloud pattern as organization. And I'm going to use the word degree of organization, for example, a lot. Okay, so organization is an important matter for climate because it happens at different spatial and temporal scales, and it is very ubiquitous. Here I'm showing organization at different scale. We have mesoscale convective system that happens at about scales of about 100 kilometers. We have tropical cyclones that gets to scales of about 1,000 kilometers, and then we also have planetary scale organized convection, for example, Madden-Julian oscillation, that has the scales of about 10,000 kilometers. Now, large fraction of cloudiness and rainfall over the tropics is associated with organized convection. For example, we know that 50% of cloudiness are due to cloud cluster or organized convection, and about 40 to 50% of rainfall is due to organized convection. And given that we know that with climate change or with global warming, clouds tend to organize even more. That makes this the matter of organized convection even more important. Now, what we can observe is that the high resolution simulations are also capable of reproducing different degrees of organization. So what I'm showing here are 2 plots that has been made using idealized simulations. So idealized simulations are, let's say, the simulations of weather or atmosphere, that they have this high fidelity. The resolutions of the model are very fine. So we have, let's say, grid sizes that are about few hundred meters to few kilometers, and that means that the model is capable of explicitly predicting or explicitly modeling deep convection. So what I'm showing here is the 3D domain of my simulation. We have x-axis, y-axis, and then vertical z-axis. The orange surface at the bottom shows the temperature, and then these gray objects, they show the clouds. So the image on the top shows the situation that convection is randomly distributed. We refer to this as random convection or popcorn convection, and convection can pop up anywhere over this domain. Now, another strong or like very extreme situation is the one on the bottom, where all of the convective clouds, they clump together in one single part of the domain, and they leave the rest of the domain cloud-free and dry. Now, this has a very large impact on the radiative cooling of these two systems into the atmosphere. For the case in the bottom, where we have a large region of our domain cloud-free and dry, the atmosphere and the surface becomes very effective in radiatively cooling into the surface. And that's one of the reasons that organized convection become a very important subject, because we thought that, okay, if organization can dry out part of the atmosphere, that can result in a stronger cooling to the space and potentially affecting or regulating climate change. I'm not going to though spend much time on the impact of organized convection on radiation, but I'm going to focus on its impact on atmospheric humidity and precipitation. So on the plot here in the bottom, I'm showing the vertical profile of relative humidity that shows that is taken by averaging over the horizontal domain in the two plots that I have on the top. So the thick line shows the relative humidity average over random convection, and the thin line shows the same average over strongly organized convection. So what we can see is that the organized convection overall has a very drier atmosphere. So relative humidity is significantly smaller compared to the popcorn or random convection. Now, this becomes even more interesting if we notice that when we redo the same plot, but only for the cloudy region, the profile becomes the opposite. So even if we average our relative humidity or specific humidity only over the cloudy region, we see that the strongly organized case has a larger humidity in that small region. So organization or the degree of organization affect precipitation in many ways. One is that because the region of cloudiness is way moister in organized convection, that can increase precipitation efficiency. So precipitation efficiency is the amount of rain that gets to the surface compared to the amount of rain that forms in the cloud. So when the rain falls, part of it evaporates into the atmosphere, and that reduces what we get at the surface. Now, if the column of the atmosphere is very humid, that means that evaporation is less and the precipitation efficiency is stronger. So the stronger the degree of organization, the larger the precipitation efficiency becomes, and the stronger rain becomes at the surface. The degree of organization also can affect how clouds interact. So when we have a precipitating cloud, we have this strong density current that form after the cloud, what we call cold pools. If those cold pools interact, the probability that a deep convection form and that deep convection becomes a strong, let's say becomes an extreme precipitation is larger. So with the tighter the clouds are packed, the more probable it becomes that precipitation becomes an extreme precipitation. And as another way that it affects precipitation is through the fact that when we have organized convection, most of our precipitation is falling in the same location. That results in an increase in accumulated precipitation, but it also has been shown to have an impact on extreme precipitation. Okay, so we can think of these two situations as the two endings of a spectrum, like random convection in one side and a strongly organized convection on the other side. Now, in real world, what we observe is that convection or like the degree of organization can be everywhere or like anywhere between these two spectrum. So another important property of precipitation is its dependency on column water vapor. So here on the left, I'm showing a plot that has been made from observational data, so precipitation from observation. This is from Nidin et al. In 2009. And what they do, they bin the column water vapor. So column water vapor is the amount of water that exists in a column of the atmosphere. Like if I could collect all of the water vapor, that gives me this W. So what they do, they bin column water vapor, and they condition that on the free tropospheric temperature. So each color shows one specific free tropospheric temperature, and they show and then they take precipitation average over each bin. So these plots are average profiles. And what they show is that precipitation has this critical behavior, and it follows, it increases with column water vapor. And at some specific threshold, it follows a parallel behavior. So it increases very strongly. Now, if we run our high resolution simulation, our high resolution weather models at global scale, we can recover the same behavior. So we can see that our precipitation, the modeled one, can also follow this parallel behavior and start increasing at some threshold very rapidly. But what is very interesting is to see that even though we conditioned our data on column water vapor and on free tropospheric temperature, precipitation shows a very large spread. So although the mean precipitation has the simple parallel behavior, if we look at all the points that falls within each bin of our column water vapor, they could be everywhere. Like precipitation for column water vapor of about 60 millimeter, for example, can be 0, or it could be about 14 millimeter per hour. Now, one interesting question here is, what explains this spread? Is it only stochasticity in the system that we cannot explain? Or is there any information that we can include in our modeling and explain the spread to some extent? Okay, so I'm gonna now talk about how climate model predict or diagnose precipitation. So we know that our climate models, they have a resolution of about 100 kilometers, the spatial resolution of about 100 kilometers, and the time step of about 15 minutes. So this schematic shows one column of my climate model. And what we can see is that all of the phenomena, all of the processes that has scales smaller than that grid size, they are not seen by the model. So they fall within the column, or they are subgrid-scale processes. The model, though, doesn't have any information about them. However, they have to somehow take into account the impact of those processes that are happening at scales smaller than the model grid. So I refer to these scales that are smaller than the model's grid as subgrid scale. So subgrid scale processes are not resolved by the model, but the model has to have somehow information about them in order to close its equation. So it's basically a closure problem. We have some terms that appear in our equation, for example, in momentum or in heat equation, but we don't have information about them. These processes then that are not resolved by a climate model or by any model, we try to represent them using parameterization. So parameterization is to represent physically or statistically a physical process that cannot be resolved. For example, deep convection for climate model is an unresolved process, or precipitation associated with deep convection is another unresolved process. So the way that we do that, we assume that this unresolved process that I call it here P, for example, precipitation, can be approximated as a function of any variable that is resolved by the model. For example, temperature, moisture, or pressure. And we call this, and this sometimes is known as diagnostic assumption, because we assume that P, or my unresolved process, can be modeled as a function of only resolved variable. That means that it doesn't matter what happens within that grid, as long as I have a mean value for the whole grid. That mean value is a good predictor for an estimation of whatever goes on in the grid. That means that if I have a structure, or if I have an organization within my grid, that metric is not directly taken into account, except if it has an impact on the mean value. Okay, so I'm showing also two examples of the parameterization of precipitation from, let's say, very earlier work by Betts and Miller. So P here is precipitation, W again is my column water vapor, WC is a critical value for column water vapor, which itself depends on temperature. And this H is a step function. Each H becomes 1 when W becomes larger than WC. So what this assumes is that if my column water vapor goes above some threshold, then whatever extra water vapor that I have is gonna rain out. So that means that precipitation is modeled as a linear function of column water vapor. Now, this doesn't take into account any information about subgrid-scale structure. It only relies on the mean profile of column water vapor. On the right, I'm showing a more sophisticated parameterization for cloud condensate, this QC. For this parameterization, the model predicts a mean value, so that resolved value for specific humidity, let's call it QT. But the model could also have a diagnostic or prognostic equation for the variance of our specific humidity. Given these two variables, then the model assigns a distribution to specific humidity, and it assumes that any part of this distribution that has a larger value than the saturated specific humidity is going to condense to form this cloud condensate. So again, this parameterization goes a little bit more into details and level of sophistication, but it's still not the variance and not the mean, depends on the structure of our cloudiness. And what is important is to remember that what we had from comparing the relative humidity for random convection compared to the organized convection, in both cases, we see that relative humidity reduces with organization while precipitation increases. So these two models may may go in a wrong direction in predicting the amount of precipitation. Okay, so I'm going to go back to the first slide that I had that I showed the shortcoming of GCM in predicting precipitation. GCM, we discussed that rain too little and too often. They have a bias toward light rain and they have a smaller predicted variance. Now, the question that I want to pose is that do we need to include some information about subgrid-scale cloud structure in the parameterization of precipitation? Okay, so the objective of my work then is twofold. First, I'm going to ask, can precipitation be parameterized using result variable? So basically, kind of like evaluating the accuracy of this equation or this approximation that I have. Precipitation approximated as a function of result variable. Can we predict the overall behavior of precipitation? And can we explain the stochasticity or the spread that we observe in our precipitation? The second part, I'm going to ask, does P as a function of, let's say, result variable and also some information about subgrid-scale structure can improve the prediction? Can we explain the stochasticity that we observe? It's still unclear how to model this stochasticity, but in the studies, they show that stochastic parameterization having great potential to increase the predictive capability of weather and climate model. In this specific case, the stochastic term comes in as a simple noise added to deterministic parameterization. Okay, so I'm going to go through the neural network and the data. The data that we use comes from an experiment called Diamond. These are global storm resolved model. They have a very fine resolution of about few kilometers. That means that they explicitly resolve deep convection and we don't need to parameterize it. I'm going to focus only on tropical bands between 20 south to 20 north. And I'm going to be comparing two scenarios where I predict precipitation as a function of resolved variable, and then I add some information about subgrid-scale structure. The way that I pre-process the data, I take this high-resolution data and I average over grids of GCM size. So I take a grid of 100 in 100 kilometer, I average, and that gives me one input of my neural network. So here, for example, I'm showing 4 inputs of my model. I have column water vapor, surface temperature, temperature near the surface, and a specific humidity near the surface. Those are the original, the high resolution data. I coarse grain them, I average over this domain that I'm showing here, and that gives me an input that has a size of about 4. Okay, so the way that I want to do this now is to replace this F with a neural network. The input to this neural network are these, what I call larger scale or resolver scale that I obtained by coarse graining my high resolution input. They goes to the neural network as input, and the model predicts precipitation as output. So we assume that if there exists a mapping between our result variable and our precipitation, the neural network can give a very accurate approximation of that mapping or that underlying function. Okay, so here is my first result. What I'm showing is precipitation as a function of column water vapor, like similar to the profile, to the plot that I had before. So the shown are in orange what the neural network predicts, and in dotted blue what I compute directly from my high resolution, from coarse graining high resolution simulation. And what we observe is that the model can kind of like very nicely capture this overall dependency of precipitation on column water vapor. And the model can also capture some of the spread. So the shading here shows the spread in both predicted data in orange and ground truth, that is my coarse-grained high-resolution data. The model captures some of the spread, but it still underestimate the spread in the data. I also compute R square. So R square shows how accurate my model can predict. If it's close to 0, that means that it is as good as a random predictor. If it's close to 1, that means that it can explain any variability in the data, or it's a perfect model. So we see that R squared is stay close to 0.4. So R squared is here computed for each bin of column water vapor. So the model has some skill, but it's not that accurate. I'm also showing the probability distribution of predicted precipitation in orange and true precipitation in blue on the right. By true, I mean the coarse grain from high resolution data. What we see is kind of the similar bias that we observed in our GCM. The model overpredicts small rains and it's missing the tail. So the strong precipitation is not reproduced by our neural network. So this means that overall, my simple neural network that has access only to resolve variable can capture this overall dependency of precipitation on column water vapor. It partially captured the spread in precipitation, but it underestimated the extreme precipitation. So tail of PDF is missing. Okay, so I have an answer to my first questions. Overall behavior can be captured, but the spread is underestimated. Now I want to look into the second question. I want to add some information about subgrid-scale structure. Now the difficult question is, if we want to inform our model about neural network about subgrid-scale structure, we have to somehow quantify and measure this structure or the degree of organization that we observe. But this is kind of very complicated task, and because the image is very rich, they have really different patterns, and we don't know how to quantify it. However, over the last 2 decades, there have been many studies on the organization of convection, and more than 25 metrics have been developed to measure the degree of organization. There is a nice paper by Johnson et al. That they collect all of these metrics in the same paper and they apply them to the data. So we use their package and we applied all of the metrics that they have collected to our data. We can categorize these metrics as a statistical, those that look at statistical properties, for example, the variance of moisture or the inner quartile distribution of moisture. They can be object-based metrics. For example, they look at the distance between the convective center, or they can be like a scale decomposition metrics. So we take these metrics and we apply them to our data. We make then the time series of these metrics. So this, let's say I have my data coming from high resolution. I have 25 metrics. I apply those metrics to my data and I build the time series of different metrics. Now, what this heat map shows is the correlation between different time series, or between the time series of different metrics. So what we hoped for here is that this heat map can hint or can tell us something about which of the metrics should be used for our to inform our neural network about the degree of organization. However, it looks more like a zoo of metrics. There isn't that much of information here that we can easily capture. There is two more important problems with these metrics. One is that they are designed for large domain. So they are designed for domain size of about larger than 500 kilometer and 500 kilometer. That means that if I apply them to a GCM size grid, they may not capture any variability. The second problem is that they target a specific aspect of organization. So this specific aspect may not be informative or useful for predicting precipitation. So we need a metric that can be useful for a small domain and that can be informative for predicting precipitation. So the way that we go around this issue is to learn an organization metric implicitly using an encoder-decoder or using a neural network. So an encoder-decoder model is, we can think of it as a PCA, but a nonlinear PCA. So it's a nonlinear dimensionality reduction machine. We pass high resolution field as input to one of the first part of this model, that is encoder. This encoder takes the high resolution input and maps it or compress it to a very low dimensional space. So here I'm going from 32 to 32 to something like 2 power 2 or 2 power 1. The decoder part then recovers that low dimensional representation. Here I call this low dimensional representation org to stay consistent with organization. So this decoder then takes the org as input and tries to reconstruct the original field that we have, the high resolution field. So if we go from this high resolution space to the low dimensional representation, and then from low dimensional representation, we go back to the high resolution or physical space. Now, we don't know what we capture here in this org space, but we know that it's a low dimensional representation of our original field, and the model use this to reproduce the original field. So whatever information exists in my high resolution field can be captured here. And if I connect this directly to my the neural network that predict precipitation, the neural network that predict precipitation can also inform this org variable about its impact on precipitation. So the way that I use this model then is to develop a 2-block neural network. The one on the left is my encoder-decoder that receives high-resolution column water vapor as input. It maps it to this low-dimensional representation that is now our org variable or our metric for measuring organization. The decoder takes that org to produce the original field, and the prediction, the network that predict precipitation on the right extract the same field, the same variable, the same org variable to predict precipitation. So my new parameterization now has two inputs, my result variable and my organization variable. And because these two neural networks are trained together, this organization, whatever it captures, affect predicting precipitation. So the neural network gives feedbacks to my encoder-decoder about how the information in org affects precipitation. So it's kind of like forced to capture information relevant for predicting precipitation. Okay, and here is my new result. So the one on the top is the result before with only result variables. And the one on the bottom is the new results where I have my encoder-decoder connected to my neural network, which predict precipitation. So again, I have precipitation versus column water vapor. We now see that the model is capable of more accurately capturing this overall behavior of precipitation. But the model is explaining now the whole spread in the data that we had. And R square is increased to 0.8 for almost all of the bins of column water vapor. On the right, I'm showing the PDF of precipitation, and we see that the tail has been accurately modeled. So this new neural network with organization information is capable of predicting the extreme precipitation. So this means that we can develop a new parameterization for our subgrid-scale organization using an encoder-decoder model, and including this organization information can significantly improve the prediction of precipitation. And we see that the stochasticity that we observed at GCM scale is then explainable by this subgrid-scale information. I also have a 2D map of latitude, longitude to show R square and how that changes with location. So here R square is being computed for each latitude, longitude grid and across the time steps. So the one on the top shows the baseline and the one on the bottom shows the neural network with organization as input. We see that we have an improvement almost everywhere, and there is still some locations like these blue parts that the model struggled to predict. We also do some sensitivity tests to see if our approach is sensitive to the size of the domain that we get. So we were averaging coarse graining over high resolution simulation, and we were averaging. I was showing the result for 100 in 100. Now we do the test for domains of 70 kilometer up to 200 in 200 kilometer. And we see that the model, the approach is not that sensitive to the resolution. We also play with the size of organization metric, or that low dimensional representation of my encoder decoder. We try 2 and 4, and the model seems to be doing a good job for both resolution. It has some reduction in its performance for the case that we reduce the latent space or the organization dimension to 2 here in black and dashed line. Okay, so now the question that I want to ask is that, okay, this information can improve the prediction of precipitation, but in a GCM, we don't have access to high resolution field. How can we get the organization metric to use it in our parameterization? Okay, so one way that we can maybe address this issue is that maybe we can predict our organization, the one that we discovered using encoder-decoder, using a neural network that has access only to result variable. So I'm introducing some new notation. This org-t now is the one that I directly extract from my encoder-decoder. Org-p is the one that I try to mimic using another neural network that doesn't have access to high resolution field. So basically what I'm trying to see is that if this information that I captured in the latent space in my low dimensional space can be recovered somehow without having access to high resolution field. So what we do then, we use this neural network, we pass as input the result variable, and we try to predict our organization metric that we discovered with encoder-decoder. And here in this plot, I'm showing how the neural network can predict this org variables. So org-t is the one extracted directly from encoder-decoder, and org-p is the one that I'm trying to reproduce using only result variable. We see that this model doesn't have that much of, this neural network doesn't have that much of skill in reproducing or in predicting my organization metric. So R square stays very low, and the plot is pretty much spread. So this is not surprising, because if we could capture the information that we have in our organization metric from result variables, we didn't have to go through encoder-decoder and look into the high resolution. We should have seen some good prediction from our baseline model that had directly access to only result. And this also tells us that there are information that organization metric that we have here contain, and that information comes from the high resolution distribution of, let's say, moisture, that we cannot recover from the result variable. Another test that we do is to say, okay, maybe there is some information about our organization metric in the previous time steps of our result variable. So basically, we assume that maybe there is a memory process that is being stored in our result variable. And if we use the memory of our result variable in our predictor, maybe we can predict our organization metric. So I'm trying to predict my organization metric of, let's say, time t by using result variable of that time, but also previous time steps. If I set my n equal to 4, that means that I'm using 1 hour of memory in my larger scale variables. I see some improvements. So this means that the larger scale contains some information about subgrid scale, but that is very limited. So my R square doesn't go above 24 for 3 of them, and it stays about 40 for the first organization. The other test that we do is that, okay, if we think about real world, we have a cloud pattern at this time. That cloud pattern is not going to be totally different 15 minutes later, but it has to somehow resemble what we have now, right? So there is this memory, there is this history that is involved, and maybe we can use that to improve the prediction of our organization metric. So now we build another model, another, let's say, data-driven parameterization that takes the takes the result variables at time t and previous time step, and it also uses organization metric of previous time step in order to predict organization at this time. So we are assuming memory that is contained in result variable, but also memory in our subgrid scale variable. And if we do that, we see that the neural network that we use to reproduce organization is doing a really good job. So R square increases to 0.95 for all of the organization dimension that we have. This means that there is some persisting structure in our high-resolution field that causes this memory. And because our organization metric is capturing that structure, we can expect that organization at time t has some strong correlation with organization at next or at previous time step. We see that organization at time t has a correlation of about 0.9 with the one at next time step, which is 15 minutes after. And this correlation reduces to 0.6 for about an hour later. Okay, we do a lot of tests to investigate the impact of memory in a spatial and in temporal data. Like, instead of only including the memory, we also include the neighborhood. For example, if there is a front coming or if there is a very large scale organization, then maybe we can capture that by including the largest scale variables, but from the neighborhood. And here I'm showing a plot that summarize how these information can improve the prediction of our organization metric. Okay, so I'm getting into the last part of my talk, what org variable captures. So when we use these encoder decoders, we don't have any control over the information that we are capturing for our high resolution field. But is there any way to somehow interpret what we learned or like discover what we are capturing in the latent space? Well, so here there is an attempt to somehow like open this this box and look inside and see what we are capturing. So what I'm showing here is an organization that we learned using encoder decoder that has a dimension of 2. So here I'm showing the marginal distribution of org1 and org2. So org1 has a very long tail, while org2 has kind of very symmetric distribution. Now what I can do, I can scan from this latent space, so I can sample from this org space, I can pass them to decoder and reconstruct the output. So the output is in my physical space. So if I see the output, I can say something about it. Like I can say if it's organized or if it's randomly distributed. So what I'm doing, I'm taking values of org1, org2 from this distribution. I pass them through my decoder, and I reconstruct a high resolution field that was the input of my encoder. And I'm scanning through this. So I'm going from org1 from the small value to large value that is here in my x-axis, and org2 from small value to large value here in my y-axis. So this first image then corresponds to a value that falls here in my distribution. And we see that the value that falls here has kind of very heterogeneous distribution. Now, if we go along x-axis and increase our org1, we see that this field seems to be more organized. So we have this very bubble moisture at the center of the domain. Yeah, sorry, and this field shows the moisture. So the dark color is a dry region, and the very light yellowish is a very moist region. So we see this blob of moisture at the center. Now, if I go through the axis 2, I see that this kind of like the contrast in my humidity changes. So we can conclude that one of these organization metric captures how heterogeneous is the field, and the other one captures the contrast in the humidity field. So we can say maybe in a simpler way, we can say in one side we capture the spread in the field, in the other side we capture the higher moment of moisture. I have a second plot that I try to like easily explain it. So here again, what I'm doing, I'm binning my org1 and org2, and for each bin of org1 and org2, I randomly sample one input or one high resolution field, and I plot it here just to show how those fields look like. And here I remove the mean, so all of them seems to have a very strong contrast, but the fact is that if I don't remove the mean, the ones that fall here have a very homogeneous distribution, so the anomalies are negligible. And then for each of these bins, I compute sigma, the standard deviation of all of the inputs or all of the high resolution samples that fall within that bin. I compute the standard deviation, and then I take the average, and this plot shows the average. So the lighter the color means that I have a stronger standard deviation. The darker the color means that the standard deviation is smaller. So basically, if it's lighter color, I have this very wide distribution of moisture. So that means that in one axis, I'm kind of capturing how spread is my moisture field. I also look at the skewness, so the third moment of moisture, and we see that in my x-axis, we see that the skewness changes strongly. I have another plot for Gini index. So Gini index measures how homogeneous is the distribution of some value. If it's 0, that means that everything is very homogeneously distributed. If it's 1, that means that there is a huge inequality in the distribution. So again, we see that in the plot shows some dependency of the org1 on Gini index as well. Sorry, the inverse Gini index shows some dependency in org1. Okay, so with that I can summarize. So what I show is that the degree of organization can be implicitly learned using autoencoder. Org-informed parameterization of precipitation accurately reproduce precipitation spread and extreme. And then subgrid-scale organization is the primary source of precipitation stochasticity at GCM scale. And then we also show that these implicitly learned org variables are temporally and spatially correlated, and org variables can be modeled as a memory process using an autoregressive model. And I also showed that the two-dimensional org variable captured the structure and the variance of the moisture field. Thank you very much, and I look forward to your comments and questions.
Brilliant. Thank you very much. This was really fascinating. Lots of interesting work. I myself have tons of questions, but I won't hog the time here. So as always, for people who are new, you can post questions in the chat. So feel free to do that. But I might kick us off with one while people do that. Which one to pick of the many? I mean, let's start with a hard one. This is super interesting, and so and you can really see how this will improve precipitation predictions. So a hard one maybe is to ask, once you do precipitation this way, how do you ensure that it sort of remains physically consistent with other model GCM fields? Say you may predict precipitation because your prediction gives you a higher degree of organization, but your cloud scheme doesn't even condense that much water, and so you would be inconsistent between the cloud and precipitation fields. Is this something you thought about already?
Yeah, that's a great question. So so this phase of the work is mostly like proof of concept. If we need to include in organization, if that has any information for improving predicting precipitation. So if we want to bring this into a climate model, we had to include it also in the deep convection parameterization. And I think through that we can impose physical constraint, for example, the amount of water that we get in our like the amount of rain that we get has to be also consistent with the moisture budget of our deep convection. Yeah, I definitely thought about that, but and it's still work in progress.
No, yeah, and that's not easy to fix as a whole. No, that's very interesting. I had a question also about the time memory, and a slightly technical question. There is a little bit that obviously introducing a memory makes a prediction better simply because you have obviously consider persistence. And the more organized the system is, the longer lived it is. And if you go on a 10-minute time stepping, a mesoscale convective system is almost perfectly predictable by persistence but it doesn't give you any predictive skill if it's organized. So does this play in here? Is it partly just persistence that gives you this strong improvement?
It's not only persistence, because if I remove the memory of org itself, and if I only include larger scale, and if I include the neighborhood as well, so that means that if I have a front or something coming, then that also improves the prediction of my precipitation. So to some extent, it is the persistence, or like to largest extent, it's the persistence of my let's say my cloud organization.
Yes. Okay. Yeah. So it's a bit of both, I guess.
Yeah, it's a bit of both. Yeah.
No, very good. I mean, I found particularly analysis also of your fields in embedded space. I think that was very insightful. Which is something I think as a community will probably look into it a lot. Is there any good lessons you can give the community on the way? Sort of, I mean, you've probably discovered some of this in hard work and really how to make use of it. I mean, sampling from the distributions and doing these illustrations, but that is still a little bit, it's intuitive to see, but it's exploratory. Can you give us some guidance on how we should approach such problems?
Yeah, so I think like it would be really useful if we can quantify this metric, like have an expression that we can simply apply to any other fields without using encoder decoders, and it, like, let's say in a very conventional way. The way that we are trying to like go around this is to project those metrics that we learn through the encoder decoder onto the conventional metrics that we have from the previous studies, to see if those metrics can be all combined in a way to better to sort of like to explain the metrics that we learn using this nonlinear dimensionality reduction. If we can do that, then that means that we have a new metrics that combines some of the other metrics and it has a better skill in predicting the impact of degree of organization on precipitation. But to do that, like what is very important is to have a data set that is like really kind of like covers a large period. So the data set that we have here has only 40 days. But for doing that work, we need a data set that has at least 1 year, so the whole season has been modeled.
Yeah, we're lucky. I mean, there's luckily lots of kilometer scale for 1 year, and there will be several decades out soon. So luckily that is now being available.
Right.
And then maybe there's a question about the scale dependence. I wondered about a little bit because you sort of set yourself with a stencil of sort of 100 kilometers in a kilometer scale model. I think at the end you hinted a little bit that you also considered more spatial inputs, but I wondered because in future, I mean, 100 kilometers sort of is where GCMs still are, but it's a bit arbitrary why. We could easily be, many of them could be at 50 kilometers, 20 kilometers, even for the very long runs and ensembles. And then the stencil size will matter a lot because sort of you vary the size, the domain of influence in relation to the scale of the organization. So then it becomes, or I could see a lot of scale dependency of an approach like this. So I wondered if you had thought about just making your sort of domain quite big to start with, and to sample from a really big domain, and then you lessen the scale dependence problem.
Yeah, that's a great point. No, I haven't tried the smaller domain. So the largest that I tried is 200 in 200 kilometers square, but that was the maximum. Yeah, that's a really great point to say, like, if we go above that, could we see something different? Yeah, thank you.
Because in a way, we're in this discussion, obviously, that there's a part of the community that thinks we won't do as much GCM parameterizations anymore because we just compute ourselves out. But then the other part thinks this has a long role to play because we can't do these long kilometer scale runs yet. But then we go really, we go into these more or closer and closer to the gray zone for the people who obviously don't think as much about it. So the zone where you partially resolve what you otherwise parameterize, and that makes it a bit tricky.
Right.
Yeah, so that's one thing that would be really interesting to do a bit. So I see here's a question also from Henrik de Abreu. How restricted is the model to the data you have available? And then the question is, did you look into data augmentation so that aims to simulating cases that are not plausible but not very common in the data set, or did you feel that was necessary?
I just reread the question to make sure I'm understanding.
It's basically the question is, do you have enough data, training data that's representative, or do you need to augment it with a data that's just not represented as well in the data set?
So we did do some data augmentation, but that was for a different purpose. So we have the rotation of our data in order to make our organization metric not dependent on the orientation of the image that we have. But in terms of like to include more scenarios in our data set, we haven't tried that, no. And I should say that, so the way that we deal with the with encoder decoder, we pass the anomalies instead of passing the absolute values. That means that my model, my encoder decoder, is not sensitive to impact of increasing temperature or, like, let's say, out of distribution data. I'm not sure if I answered the question. I cannot never guarantee that for the moment, for the approaches that we have, we can never guarantee that a neural network can generalize to any unseen situation. There is a chance if we add some constraint, like, for example, invariances through the latent space, there is a chance that they generalize better, but it's not guaranteed.
Yes, no, and that's true. I mean, you hinted already to a case. It's a 40-day run, and you don't cover all seasons yet. But yeah, it would be probably a big ask to predict seasons from the limited training data that you have. No, that's very interesting, and I think we're almost approaching also the end here. So I thought this was super interesting as a talk, and I think it's something that where the community, I think we'll probably have to follow up on a lot of these things because it's very interesting and will have a big influence. So thanks so much for joining us. This was fantastic.
Thank you for having me.
And thanks everyone else for joining. I should say before we go that, as I said, we're kicking off, this is the start of a long and exciting series again. So we're going from between now and to the new year. And our next speaker will be Stefan Rasp from Google Research, and he will talk about Weatherbench 2 and the second revolution of weather prediction. But thanks a lot again, Sarah, for a really, truly inspiring talk.
Thank you so much. Have a great day. Bye.
And back to the team.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.